Take a moment and think, what is sound? Well, it has to do with coming from speakers or things like speakers. And it has to do with things like ears. But what's in between the speaker and the ears? Well, they're wireless in a way. It's just air between the speaker and the ears. So what about it? Well, it's vibrating, right? And how does the air vibrate? Well, the speaker's shape is designed to shove the air back and forth, crunch it together, and to pull back, increase pressure and decrease pressure. And on the other end, the ear is shaped similarly to catch all of those fluctuations in air pressure between the speaker and the ear. And so sound is fluctuations in sound pressure. And our ear, or the microphone, moves back and forth, hopefully, in exactly the same way or something close to it, so we can reproduce that sound. If they're moving in the same way, but they're not writing it down exactly, not measuring it, they're just mimicking each other's movements, this is what we call an analog representation. One is an analogy of the other. This is in contrast to a digital representation, where the values are represented in digits, measured as numbers. So let's look at a simple wave. Here's a sine wave. It's considered the smoothest, most pure sound. We'll see some reasons why that's the case over time. Maybe you remember from a math class how a sine wave is related to a circle. As a point moves around a circle, if we look at it only from one direction, it moves up and down like a sine wave. We could consider just the vertical aspect of it and see it move up and down smoothly. We can change our grid and see it move up and down as our dot moves around in circles. And then we get back to our sine wave. Pretty smooth over and over again. So let's look at the anatomy of a wave. We can see that it's a repeating pattern. And if we look at this much of the wave, we can see it includes one positive portion where it goes above zero, one negative portion where it goes below zero, comes back to zero, and then it repeats itself. This portion of a wave where we catch every part of its pattern before it repeats, we can call one cycle. And it really doesn't matter where we start, but as long as we capture every part of it, that's one cycle. A change in phase to us sounds like no difference unless it's combined with other sounds, and then they start to emphasize and cancel each other out. If we had one sine wave that started just like this, and we had another sine wave that was going like this, slightly out of phase from the first sine wave, well, they would be added together, this one plus that, literally amplitude at each point in time, and they would add up to this, something slightly higher and something that has a phase that's somewhere in between the two. Instead, if we added our original sine wave to a sine wave that was 180 degrees out of phase, and we describe a whole cycle as 360 degrees, just like we're going all the way around a circle. So if we start with that original sine wave and we fade in the signal that is 180 degrees out of phase with it, well, all those points add together to be zero. This plus that at every point in time is going to equal zero, and so we can see them cancel each other out. This is our oscilloscope. Let's see how we can zoom in on just one cycle. We can measure one cycle of a wave in terms of milliseconds. And so, well, the unit Hertz, or Hertz, is named after Heinrich Hertz, the late 19th century German physicist. But it refers to a unit of going up and down each second. That's 1 Hertz. Well, if we were going 1 Hertz, it would take 1 whole second to go up and down. The length it takes to complete one cycle in time we call the period of a wave. And so, well, let's see. Here we're dealing in milliseconds. There's 1,000 milliseconds to 1 second. Here we're going to do something 100 times in that 1,000 milliseconds. So 1,000 divided by 100 cycles is going to give us a period of 10 milliseconds. Okay, so now I've got one whole cycle here at 100 hertz, and its period of one cycle is 10 milliseconds. What happens if I double the frequency? Well, I'm getting twice as many humps in here, or its period is half as long. But there we go, 200 hertz, a period of 5 milliseconds. So we have three ways of measuring a wave. We can count cycles, and so here's one cycle. We can count how long it takes to complete one cycle, that's called the period. That's usually measured in milliseconds. Or we can say, given a window of 1 second, how many cycles can we complete within that 1 second? So we call this the frequency. How frequently does it repeat its pattern? So let's talk a little bit more about the anatomy of a wave. What other parts are there? The points where it's the maximum distance away from the zero line. The zero line is equilibrium. If there was no sound happening, that's where it would be at rest. The farther it is away from equilibrium, the greater the sound is in what we call the amplitude. You might remember from physics class talking about a crest on the positive end, or a trough at the negative end. In audio, we can't hear the difference between the positive side of a wave and a negative side of the wave unless it's interacting with other sounds. And so we only care about how far it is away from zero. And it doesn't matter which direction it's going. We still call it a peak. But there are a few ways we might mean amplitude. It depends on the context. Sometimes we're measuring a wave as it goes along and we want to know the amplitude at a particular instant in time. And so we might be referring to the instantaneous amplitude. Other times we might be talking about the maximum amplitude of a whole cycle. Other times we might be zooming out and think about how that amplitude changes over a longer period of time. And so we might talk about the general shape or envelope of that amplitude, the amplitude envelope. Now you've probably noticed that when we change the frequency of a sound, it corresponds to what we might call musically the pitch. A high frequency corresponds to a high pitch. Low frequency corresponds to a low pitch. The amplitude corresponds to loudness. What many of our devices would call volume, but volume is really length times width times height, and that's more poetic of a unit than is useful for us, so loudness is a less problematic term. But yeah, we mean volume. And so as it approaches silence, we have a very low amplitude. If I multiply it by 0, everything times 0 is 0. Multiplying by 1 gives us full volume. Everything in between scales the amplitude and scales the loudness that we hear.